Section 1 Introduction. We're going to talk about foundation models, which are large networks, often based on transformers, that are trained on a vast amount of diverse data. These models have been instrumental in advancing deep learning, particularly in natural language and vision tasks. One of the key features of these models is that their performance can be predicted when we scale different aspects of the model, such as the number of parameters, training characteristics, and the amount of data or computation used. This predictability is captured by what we call scaling laws, which allow us to accurately forecast a model's performance based on its high-level parameters like size, data, and computation. At the same time, there's been a push towards making these large models more efficient, primarily due to computational costs. This is often achieved by using compressed parametrizations through quantization or sparsification during inference and/or training, which can lead to faster real-world performance through both software and hardware support. However, we don't fully understand how these compressed representations, particularly parameter or weight sparsity, affect the scaling behavior of foundation models, especially when we use powerful but costly training-based compression methods. In this paper, we aim to fill this knowledge gap by studying how sparsity relates to the scaling laws of foundation models. We're particularly interested in weight sparsity, which refers to networks where individual connections are pruned, and we're focusing on transformer family models for both vision and language domains. We're using the massive JFT4B datasets, which are significantly larger than what most sparsity studies have used so far. In this large dataset regime, dense models continue to improve with prolonged training, so it's currently unclear whether sparse models can outperform them when we use equal amounts of training computation. To understand the benefits or drawbacks of sparsity in this large dataset regime, we develop joint scaling laws that relate a network's sparsity, its effective size, and the amount of data used for training. We show that the validation loss, which we'll call L, can be approximated by a formula that involves the sparsity S, the number of non-zero parameters N, and the amount of training data, steps D. This formula applies to both vision and language tasks. This formula captures the power law scaling in terms of capacity, i.e., sparsity and non-zero parameters, and data. It also includes a lower bound on the achievable task loss. The first part of the formula captures the impact of sparsity, expressed as remaining density, 1s, which follows a saturating power law with certain coefficients and constants. The other parts of the formula scale the non-zero parameter count n, and the data d term, as is common in classical scaling laws. We've validated this formula empirically using large vision and language datasets, several model sizes, amounts of training data, and sparsity levels. This formula allows us to gain new insights into both the power and limitations of weight sparsity in the foundation model setting. For instance, it suggests that sparsity affects each model size in a similar way, and that sparsification doesn't significantly interact with the data scaling. We can also use this formula to derive the optimal sparsity for a given inference size and training budget, which allows us to predict where sparsity could provide benefits over simply rescaling a dense model and extending training. Our analysis shows that the optimal sparsity increases with longer training. While optimal dense models define a line on the parameter flop surface, optimal sparse models form a half-plane, with different sparsities unlocking multiple optimal sizes for a fixed training cost. We also find that pruning well-trained dense models is more efficient than training from scratch if dense checkpoints already exist, but it's significantly slower otherwise. In conclusion, our results provide the first scaling law for characterizing the impact of sparsity on the performance of transformers trained on massive datasets. This gives us a simple tool to understand the power and limitations of sparsity for a given task-model combination. It can also be used to determine whether sparsity can be a reasonable option for speeding up inference or training, in settings where specific software-hardware support for such compressed representations is available. Section Summary. Foundation models, which are large transformer-based networks trained on massive amounts of general data, have shown predictable performance when scaling various attributes. However, the impact of compressed representations, particularly weight sparsity, on the scaling behavior of these models is not well understood. This paper addresses this gap by studying the relationship between weight sparsity and scaling laws in transformer models for both vision and language tasks, using large datasets. The authors develop joint scaling laws that relate sparsity, effective size, and training data, and show that sparsity affects model size as a multiplicative constant, while not significantly interacting with data scaling. They also derive the optimal sparsity for a given inference size and training budget, and find that the main conclusions hold for hardware-friendly sparsity patterns. Overall, this work provides insights into the power and limitations of weight sparsity in foundation models, offering a tool to understand its impact on performance and determine its feasibility for speedups in specific settings. Section 2: Fair evaluation in the presence of strong scaling. We're going to discuss the importance of fair evaluation when dealing with modern transformers that are trained on massive datasets. Traditional evaluation methods, which work well for standard pruning benchmarks like ResNet 50, ImageNet, or BERT/GLUE, need to be rethought to ensure meaningful comparisons. This is because transformers trained on large amounts of data behave differently in terms of scaling. Let's break this down. 1. Training data. In a typical setting like ResNet 50, ImageNet, if you increase the training time of the dense model significantly, you'll quickly run into overfitting. However, with VIT/JFT, performance improvements only start to plateau after a very long training time, and overfitting is almost non-existent. So, if you sparsify a VIT pre-trained on 100 million images over another 100 million images, a standard setup for RN50 ImageNet pruning, you shouldn't compare it against the initial model because the sparse version has had twice as much overall training. The correct reference point would be a dense model trained on 200 million images. But this dense model will likely be more accurate. 2. Model size. Creating small yet accurate dense models used to involve arranging many custom modules into a carefully engineered architecture. If you simply scale down a 25 million parameter ResNet 50 by a factor of 10, you won't get a competitive 2.5 million parameter ImageNet model. That's why most pruning papers don't compare against such a variant. But when dealing with transformer models and massive datasets, basic width and depth scaling usually results in a strong family of differently sized models. So, it's crucial to always compare sparse models with a dense version of equivalent parameter count. 3. Computational costs. When you consider both training data and model size, you arrive at the concept of compute efficiency. This is often overlooked in classic sparsity benchmarks because training is cheap enough to reach full convergence on all models. However, a smaller transformer trained for longer can outperform a larger one trained with the same budget, i.e., for fewer steps. This makes proper comparisons even more difficult. For instance, a 50% sparse model obtained from pruning a model that was pre-trained for 100,000 steps should be compared to a twice smaller dense model trained for the same compute, i.e., 200,000 steps plus the computational cost of pruning. In a fair foundation model pruning setup, sparsity shouldn't be able to leverage increased training time, a significantly better optimized dense base architecture, or more training compute. If it does, comparisons would unfairly favor sparse models, since equivalently sized dense versions couldn't fully exploit their strong scaling properties across all these axes. It's currently unclear whether weight-sparse foundation models can win at all in this highly challenging setting, where all these factors are properly accounted for. Answering this question will require a full understanding of the joint scaling between sparsity, model size, and training data, compute, which is what we're starting to explore in this paper. Next, we'll discuss the scaling laws for parameter-sparse transformers. We'll briefly summarize the setup of our main experiments, which involve extensive sweeps across sparsity, size, and data, and use this to develop scaling laws. A detailed discussion of all our choices, including hyperparameters, can be found in the appendix. In terms of models and datasets, we focus on vision transformers trained for multi-label image classification on the JFT4B dataset, which consists of 4 billion images, as well as encoder-decoder T5 models, improved 1.1 version, trained for masked language modeling on a dataset consisting of 150+ billion tokens. We follow the model's respective original training recipes and carry out sparsification during training via gradual magnitude pruning, using a cubic schedule starting at 25% of training and ending at 75%. We've designed a grid of parameters that we sweep over. For VITs, we consider 7 target model sizes in 2x increments each, while we use 4 target sizes in increments of 4x for T5. Vision transformers are trained for 4 different lengths, with the longest corresponding to approximately 1.8 billion images. Language models are trained for 3 different lengths up to approximately 65 billion tokens. The set of sparsity targets is the same in both cases, corresponding to 2, 4, and 8x compression rate. Overall, the VIT grid was designed to be more extensive, whereas the T5 setup was chosen to be more efficient. We execute all runs in the above grids and record the resulting validation losses. This data is then used to fit parametric scaling curves. Section summary. In the context of training transformers on large datasets, traditional evaluation approaches used for benchmarking other models may not be suitable. Transformers trained on massive amounts of data exhibit different scaling behavior, making it necessary to reconsider evaluation methods. Factors such as training data, model size, and computational costs need to be taken into account to ensure fair comparisons between sparse and dense models. It is currently unclear whether weight-sparse models can outperform dense models when all these factors are properly considered. Section: Dense scaling. Let's talk about dense scaling. It's widely accepted that the pre-training validation loss of dense transformers can be modeled using a specific formula. This formula takes into account the number of parameters, n, and the amount of training data, d. The formula looks something like this. The loss equals the sum of two terms, each raised to a certain power, plus a constant. The first term is a constant divided by the number of parameters, and the second term is another constant divided by the amount of training data. The constant at the end represents the inherent unpredictability of the modeling problem and sets a lower limit on the loss. The exponents in the formula, which we'll call b_n and b_d, are usually quite stable for a specific task. However, the constants in the numerator of each term, a_n and a_d, can change with minor alterations in the process, like using a different architecture or optimizer. This formula assumes an ideal training setup with no data repetition and focuses on modeling the non-bottlenecked regime, meaning situations with enough steps, data, batch size, and so on. We're not focusing on edge cases here. We're also specifically looking at the pre-training loss and infinite data setting to evaluate how effective sparsity is in its most challenging and useful application. Now, let's move on to some preliminary observations. We're interested in understanding how parameter sparsity, S, fits into this core scaling relationship. It's not immediately clear how S should be incorporated into the formula to form a new equation, where n now represents the number of non-zero parameters. To get a better idea of what we should expect, we conducted a T5 sweep and visualized the results. We noticed three main things from these graphs. 1. The loss versus non-zero curves for all sparsity levels seem to form almost parallel lines, differing mainly in the intercept. 2. The higher the sparsity, the lower the loss, but the gains are quickly diminishing. 3. The overall shape of all curves is very similar for each training duration. The y-axis just tends to shift a bit downwards with more training steps. Based on these observations, we can construct a new formula for the joint scaling law. The first observation suggests that the model size power law scaling for all sparsity levels differs mainly in a constant factor. The second observation suggests that this sparsity factor can be modeled as a quickly saturating power law. The third observation indicates that sparsity and data scaling are mostly independent, so we keep the original d term. In summary, our new formula for the joint scaling law looks like this. The loss equals the product of two terms, each raised to a certain power, plus a third term raised to a power, plus a constant. The first term is a constant times 1 minus the sparsity, raised to a power, plus another constant. The second term is 1 divided by the number of parameters, raised to a power. The third term is a constant divided by the amount of training data, raised to a power. To properly model that 0.75 is twice as sparse as 0.5, we define the sparsity power law part via the corresponding compression rate 1s. Also, a_n is subsumed by a_s and c_s, leaving 7 free parameters. Our scaling law combines a capacity limit term, made up of size and sparsity, with the standard data limit term. This formula suggests that higher sparsity is always better, but the improvements may quickly saturate. In practice, this may not always be true. For very high sparsity, we sometimes see slightly worse performance, likely due to imperfections in the pruning and optimization process. This could potentially be modeled by a quadratic, but for now, we treat this as a bottleneck case that we do not necessarily capture. Lastly, when S equals 0, we recover the established form of the loss equation. Section summary. the authors establish a scaling relationship for dense transformers, which models the pre-training validation loss in terms of parameter count and amount of training data. They observe that the loss versus hash non-0 curves for different sparsity levels form parallel lines, with higher sparsity resulting in lower loss but with diminishing gains. Based on these observations, they propose a joint scaling law that combines a capacity limit term, size and sparsity, with a standard data limit term. Section T5, C4 Results. We'll now discuss the results we obtained from our T5 and VIT JFT4B models. Starting with the T5 model, we adjusted the coefficients of L, S, N, D to fit our entire T5 data. This was done by minimizing the Huber loss of the logarithm of L, with a delta value of 0.001 to ensure robustness against outliers. We used the BFGS method and started from multiple random points. When we compared our predictions with the actual data, we found a close match, which shows that our model is compatible with the observations. We also tested the model's extrapolation performance by reducing a 2.3 billion parameter model to 75% sparsity. This resulted in approximately 6.75 times more non-zero parameters than the maximum in our fitting data, a similar level of extrapolation as was done for the chinchilla model. To avoid any architecture bottlenecks and achieve better training utilization, we used the T5XL architecture and trained with a batch size of 256 for 250,000 steps. Despite these changes, our model's prediction was quite close to the actual validation loss. Moving on to the VIT JFT4B model, we executed the VIT sweep listed in the table and also fit a scaling law of the same form as for the T5 data. Here we used a delta value of 0.01 and did not take the logarithm of L, as we found that the NLP optimized settings from before excluded outliers too aggressively for VIT data. This sweep contained more than twice the number of data points, leading to more robust coefficient estimates. When we compared the predicted and actual loss vs data curves, we found that our model matched the collected data points very well, except for at the lowest amount of training where some points were a bit off the prediction curve. We suspect this may be due to these runs involving comparatively fewer training steps, which may have slightly bottlenecked the optimization process. One interesting feature of the joint scaling law we derived is that it allows us to easily compare models with different sparsities but the same number of non-zero parameters and training cost. This means we can determine when sparse models are better than dense ones. We defined the optimal sparsity as the sparsity value S that yields the lowest validation loss for a fixed number of non-zero parameters N and fixed training cost C. We calculated the training costs in two ways: A. Densely, as the cost of training a dense base model of size N, 1S, for the same amount of training steps, or B. Sparsely, as the actual flops spent to produce the sparse model, assuming that sparsity can be perfectly exploited during training as soon as it appears. We then determined the performance of a sparsity S model trained for compute C by querying L with D_S, which is the D corresponding to C scaled down by the increase in training costs of the sparse model. Differentiating with respect to S gives the contour line for which sparsity S is optimal, i.e., achieves the lowest loss among all possible sparsity choices, when training for the same compute. An interesting property about this contour is that it implies D_S is proportional to N raised to the power of B_N divided by B_D. This means that if data scaling is stronger than size scaling, then the same sparsity is optimal for a smaller data to size ratio on larger models. This makes sense as a process bottlenecked more by capacity than by data will benefit more from increasing the former, for example, by adding sparsity. Finally, we want to point out that the optimal sparsity can often also be determined explicitly by solving for S. For example, here for dense training costs with C_mul S equal to 1 divided by 1S, the optimal sparsity S_opt N C can be calculated using a specific formula. Section Summary. In this section, the authors present the results of their experiments using the T5 and VIT models. They fit the coefficients of a scaling law to their data and evaluate the quality of the fit by comparing actual and predicted values. They also discuss the concept of optimal sparsity, which refers to the sparsity value that yields the lowest validation loss for a fixed number of non-zero parameters and training cost. They provide a formula to calculate the optimal sparsity and explain its implications. Section: Empirical Results. Let's delve into the empirical results of our study. We've calculated the optimal sparsity curves for our experimental data from T5 and VIT models, which we previously used to fit scaling laws. The figures show the optimal sparsity contours for both dense and sparse costs. An interesting aspect of our equation is that all sparsity contours are parallel to what we call the chinchilla compute optimal line. This line represents the ideal use of training flops for fully dense models, which is clearly visible in our plots. However, it's important to note that this line doesn't always correspond to the case where sparsity equals 0, as there may be instances where non-zero sparsity is optimal, especially for sparse flops. The main takeaway from these results is that as training duration exceeds that of the chinchilla model, increasingly sparse models become optimal in terms of loss for the same number of non-zero parameters. This is because the benefits of further training dense models start to diminish at some point, allowing sparse models to surpass them. We've illustrated this effect using a subset of our actual VIT data. So, how much longer should the training be? For sparse flops, 50% sparsity is already optimal for less than double VIT and less than triple T5, the training duration of chinchilla. For dense flops, it's approximately 5 times and 70 times, respectively. While the latter number may seem high, it's worth noting that language models of the sizes we're considering here are typically trained for over 100 times longer than chinchilla. Moreover, larger models are being trained with increasing amounts of data, for example, Llama 2-7b with approximately 14 times chinchilla. In general, the optimal sparsity at a given point is lower for dense than sparse flops, as the former assumes that sparsity provides no benefits during training. In the previous section, we focused on when sparse models become optimal, but not how much better they can be compared to dense models. We've explored the question: how much larger, and thus computationally more expensive, does a dense model need to be to match the loss of a smaller sparse model with very long training? We've found that a 75% sparse VIT with n non-zeros will perform similarly to a dense one with approximately 2.17 n parameters, when both are trained with the same amount of data. This holds true for any amount of data and thus also in the infinite limit when training is purely capacity bound. This suggests an equivalence between dense capacity and sparse capacity. Interestingly, sparsity gains are very similar across vision and text domains, with the sweet spot being around 75% sparsity at around approximately 2.15 times gain. In addition to our previous exploration of unstructured sparsity, we've also considered structured n-m sparsity, which can be well accelerated on actual hardware, for example, as 2-to-4 sparsity on modern NVIDIA GPUs. We've found that minor changes in the process only affect the sparsity term. This can be exploited to fit laws based on significantly fewer runs. We've applied this in the context of n-m sparsity by fitting new laws for 2-to-4 and 1-to-4 as well as 4-to-8 and 2-to-8 patterns, based only on a subset of our full grid. The collected data displays a very similar form to our previous results, indicating that the general scaling law shape also holds for n-m sparsity. In general, it seems that 2-to-4 and 4-to-8 perform both very similar to 50%, although the n-m estimates are likely slightly more noisy due to less data used in fitting the curves. Meanwhile, 1-to-4 brings almost no advantage and 2-to-8 only a slight improvement, which is contrary to our unstructured results. We suspect that the 75% patterns may simply be too stringent to significantly increase capacity beyond their 50% variance. Section summary. The empirical results show that as training time increases significantly beyond the point of optimal dense models, sparse models with lower sparsity become more optimal in terms of loss for the same number of non-zero parameters. For sparse flops, 50% sparsity is already optimal with less than 2 times longer training than dense models for VIT and less than 3 times longer training for T5. Additionally, the study explores the performance of structured n-m sparsity, finding that 2-to-4 and 4-to-8 patterns perform similarly to 50% sparsity, while 1-to-4 and 2-to-8 patterns bring little advantage. Section 4.2 Pruning Pre-trained Models. In this section, we'll discuss the process of pruning pre-existing, well-trained models to make them more efficient. We're particularly interested in comparing the efficiency of starting from scratch versus starting from a pre-trained checkpoint. To do this, we trained 3 models, VIT S16, M16, and B16, for 4 full epochs on JFT, which is equivalent to 16 billion images. We then began the gradual sparsification process from these checkpoints, using only 5.6% of the pre-training budget. Since the model was already pre-trained, we started to sparsify immediately rather than after 25% of training. We then used our scaling laws to determine how much training would be necessary to produce equivalent models of the same quality when starting from scratch. Our results showed that if the model already exists and there is no pre-training cost, starting from a checkpoint is more than 4 times more efficient than starting from scratch for 0.75 sparsity, and more than 2 times for 0.875 sparsity. However, the efficiency gains decrease with higher sparsity, likely due to the increased divergence from the initial starting point. When the pre-training cost is included, pruning throughout the whole training process appears to be at least 4 times more efficient, relative to the approximately 5% pruning of pre-training budget. We also found that models with 50% sparsity are approximately 0.2 to 0.3 points away from their dense baseline loss, which aligns with our previous findings that the size gain of 50% sparsity is noticeably less than 2 times for well-trained models. The concept of sparsity and pruning, which involves having a large number of exactly 0 weights that can be ignored during inference, has a long history. Current state-of-the-art methods range from simple gradual removal of the smallest weights to more complex methods. However, most of these works focus on relatively simple tasks with overparameterized models. In contrast, there has been little work on sparsifying modern transformers trained on massive datasets. Some studies have shown that sparse models can outperform dense ones, but it remains unclear if this can also be done on more recent, smaller, and much less undertrained networks. The success of transformer models is largely due to their exceptional scaling properties. Increasing model size and/or data consistently improves performance, even at a large scale. This scaling behavior is very predictable and follows relatively simple power law curves. However, not much is known about the scaling of weight sparsity for such models. Finally, making transformers more efficient is a highly active area of research. The most popular and practical approach is quantization, which reduces the numerical precision of weights. There are also many works on mixture of expert (MO) models, which are a form of dynamic activation sparsity. In general, quantization, MOs, and weight sparsity are all complementary techniques that may be combined for compound gains. Section Summary. In this section, the authors discuss the efficiency of sparsifying pre-trained models compared to sparsifying from scratch. They train VIT models on a large dataset and then apply a gradual sparsification procedure. The results show that starting from a pre-trained checkpoint is more efficient than sparsifying from scratch, but the efficiency gains decrease with higher sparsity. Additionally, the authors mention that weight sparsity is a different approach from quantization and mixture of expert models, but these techniques can be combined for further improvements in efficiency. Section: Limitations. In this section, we'll discuss the limitations of our study and how it aligns with other works, as well as the practical implications of our findings. Firstly, let's talk about the limitations. Despite conducting extensive experiments in both vision and language domains, there are still areas that need improvement. Our sparsification method was designed for robustness and scalability across various setups, not necessarily to maximize performance in a specific one. We believe that the general trend of our scaling results will remain the same, but there's room for improvement in the specific coefficient values. This could be achieved through more detailed tuning for each run or better sparsification techniques. In this study, we pruned directly for large-scale data pre-training tasks. This is beneficial in terms of usability, as all downstream applications would benefit from a more efficient base model. However, this approach makes compression quite challenging. We believe that sparsity rates could be improved significantly if pruning is performed directly for more specialized applications that only require a subset of the base model's full capabilities. We also considered the optimal infinite data setting, which essentially eliminates overfitting from dense baselines. We believe that sparsity could be particularly useful when data is limited and has to be repeated. Lastly, our main goal was to understand core scaling relationships, so we focused primarily on the most straightforward performance metric, the non-zero parameter count. However, in practice, sparsity acceleration can be quite complex. Current software, hardware may not provide ideal speedups, and models generally also contain operations, like layer norms, attention, which do not benefit from weight sparsity. Extending our results to different target metrics is an interesting topic for future work. Now, let's discuss how our scaling insights align with existing sparsification results on similar models, datasets. The results in the appendix of a decoder-only text generation model are consistent with our scaling laws. The improvement through sparsity appears to be similar for each model size, and their maximum size advantage of 2.5 times observed at 0.9 sparsity is quite close to our limit gains. In contrast, another study reported a significantly better gain of approximately 5 times, but in a different setting where the baseline is training compute optimal and sparsification uses more than 5 times more data than the dense comparison point. This is not inconsistent with our results. If we apply our fitted T5 scaling law to this setup, we predict a smaller loss for the longer trained sparse model. Lastly, Sparse GPT notes that post-training pruning becomes significantly easier as the model size increases. However, they do not perform any retraining, and observe this effect primarily relative to the respective unpruned base model, not in terms of improvements over the size vs loss frontier that we study in this work. We believe that this is likely more related to the pre-trained model's initial robustness to perturbations rather than the architecture's inherent sparsifiability. Finally, let's talk about the practical implications of our findings. Sparsity seems to affect each model size in approximately the same way, while remaining mostly independent of the amount of training data used. This suggests that good pruning performance in less expensive settings should generalize to performance at scale, which will hopefully accelerate research on new sparsification recipes and algorithms. We have also shown that optimal sparsity levels continuously increase with longer training. Sparsity thus provides a way to further improve model performance for a fixed final parameter cost. In particular, when training beyond chinchilla optimality, where simple dense training starts to run into diminishing returns, sparsity can provide a clear alternative. Thus, our findings can be interpreted as providing practical motivation for further developing sparsity support. We would like to express our gratitude to Suvinay Subramanian for his useful feedback and suggestions, especially regarding certain sections of our work. We also extend our thanks to Amir Yazdanbash, Shivani Agrawal, Jeffrey Pennington, and Jan Dauphin for their valuable feedback during our discussions.